Okay, so now we'll get into mechanical behavior testing and manufacturing properties of our materials. So this is my second keynote for your, I believe this is chapter 2. Yeah. All right, manufacturing processes, they definitely involve shaping, okay, materials. That's what we do when we manufacture something. We shape the materials. With what? By plastic deformation, okay? So plastic deformation is what we're trying to do is, like we're applying the mechanical forces to be able to shape the materials. Because when you think of the materials, they are like metals. They can be different kinds of materials, right? Alloys, we have different kinds of alloys, composites. We have wood. We have plastics. Even in plastics, we have different plastics. Some of them are thermal plastics, and the other ones are thermosetting plastics. So whatever your material is, you've got to apply mechanical forces in order to, to shape them. Okay, and that's what we're talking about, the deformation. So the mechanical properties you've got to deal with in manufacturing. So I list all these important for you, and that's your strength. We call it the yield strength, and the symbol is Y, but I call it just strength, and you understand that's yield strength. And sometimes you're going to come into contact with ultimate tensile strength, right? It's one of the mechanical properties. And we have modulus of elasticity. Again, I call it modulus. Symbol is E. Another mechanical property, ductility, and this is something some of the students have trouble with. You gotta feel it, okay? That's what I told you several times in class. Is flexibility, yeah? And we deal with total elongation. If something isn't flexible, you cannot make it to elongate, yeah? So total elongation, and also you cannot make it to reduce. So that's how you gotta feel what ductility is. So your total elongation, reduction of area. So these are the aspects in ductility that we deal with. The next mechanical property is your hardness, and everybody laugh at me if I say that, but it's very important, yeah. And energy, yeah, that's another mechanical property. So everything that you have to deal with force is mechanical, yeah. In fact, energy, when we talk about energy, it's not other types of energy, but something that's you required to for plastic deformation, okay. So this stress force, yeah. So we'll talk about the energy that is required for plastic deformation. So in order to deform a material, you need to apply energy. Okay, that's some form of force. Then, when you think about the mechanical properties, we see they depend on these things. The first one is they depend on the material itself, material condition, meaning the conditions of the material, temperature, the temperature of that material, deformation rate, how fast or slow, right, the material can deform, and the surface condition of that material. And of course, our environment is something you can't be able to get rid of because we are in it, okay? All of your material, all of your manufacturing processes, all of your technology, machinery, everything is in the environment, yeah? Again, all of this really important, and that's what mechanical properties depend on. Tensile test. Alright, so this is a test, and you are testing tensile, which is your strength. Very simple. We commonly use it to determine mechanical properties, and you can construct the true stress and true strain curve. Okay, and in the pictorial final exam review, I put some pictures for you, so you have like at least one time to view them. If I tell you to read the handout or read the text, but sometimes you skip them. It's really important. And in there, you can be able to see what true stress and true strain curve looks like. And every time you come across that type of curve, you ought to know you're dealing with tensile test. So this test can be able to make true stress, true strain diagrams or curve. Okay, so this curve, what does it do? It determines strength coefficient, your K, your little n, so strain hardening exponent, and we have already dealt with them in n equation. Okay, strain rate, sensitivity exponent, and that's your m. And the next one, toughness of your materials. Every time I talk about toughness, I tell you to remember your friction. Okay, so that's with your true stress and true strain curves. So every time you think about these curves, then you know that we're trying to get these variables. Okay, or you can also call them parameters. So strain coefficient, strain hardening exponent, and we have a strain rate, sensitivity exponent, and then the last one is your toughness. Compression tests, they are subject to inaccuracy, and that's because of the presence of friction, resulting in barreling. So this is another type of defect of the specimen. So what this is saying is you can't, I would say like the compression tests is not perfect. Why? Because they can be inaccurate, meaning like not as good. And that's because of friction. That's because of the presence of friction, and that friction is causing some sort of a barreling. Okay, in the specimen, that's just a test specimen that we're talking about somewhere around here. When we do the compression test. Another test for mechanical behavior, your torsion test. Everything in mechanical property got to do again with force. So torsion test is conducted on tubular specimens. Specimen again, just a test, blank or material, and it is subjected to twisting. Okay, so in this test we call it the torsion test because we twist the specimens. And see if how much it can stand, how strong it is. Bending, flexure tests. So what are we doing here? We bend, of course. So it's the name. So we commonly use that for brittle materials. Test the brittle materials, and we determine the modulus, of rupture and a transverse rupture strength, right? Most of the tests in mechanical properties, again, we're dealing with how strong they are, so looking at their strength. Hardness. It is used to do what? To determine the resistance of your material, that's your test specimen, to permanent indentation, or to scratching. So we want to know like how resistant that material is to indentation and to scratching. Permanent mean like it's not going to reverse, meaning like these indentation and scratch, they're going to stay in that material, and we want to determine, okay, that resistance of the material to them, and we call the hardness test. Again, telling you many times, mechanical property tests in the mechanical properties, they are related to strength. They are related to wear resistance, okay, of that material. We want to see how strong they are. And of course, hardness tests, they're not a fundamental property. Okay. I meant hardness. What I want to say is hardness, this is not a fundamental property. Alright, the next one is a fatigue test. Another one for strength, so indicate endurance limit, a fatigue limit, again, of your test specimen or your material. So because some materials, they have no endurance limit, okay, they can be able to mean like it can stand, but some of the material, they have that endurance limit, and we want to know what that is. Yeah, so we do this test so we can be able to find that endurance limit. You know the name again, fatigue limit, right, of that material. So what's the fatigue limit? You got to know what this is, because that's what you're testing for. So the maximum, again, your max stress to which a material can be subjected. So when you think about the stress, and in other words, we already talked about, right? Stress, you have learned, thus you have applied load, right? And every time you think about the stress, you know there is an applied load, so therefore that material can be subjected to that load. So we want to know what's the maximum stress, okay, it can be able to subject it. And I would call it like right before the fatigue failure, right? So before your failure happens, that's your max stress. It doesn't matter what your number of cycle is. So anyway, test the fatigue limit. We're looking at the max stress that the material can be subjected, and again without fatigue failure, okay? Or I will call it again just before the failure. So that is going to be a true maximum stress. Allowable stress, so something that you have to know, and that's for materials. So we have two different materials. One is with the endurance limit, and the other one is without it. So for these materials without the endurance limit, so for example, aluminum, it doesn't have an endurance limit, okay? For them, you've got to report, okay, allowable stress. And you got to do it with the number of loading cycles. So those material with the endurance limit, we don't care what the number of cycles is, right? Therefore, the material without the endurance limit, it must be reported, okay? This allowable stress must be reported with the number of loading cycles, okay? So it depends on the loading cycle, and don't forget that. We all know what creep is. So those of you may have taken industrial material, so you know what creep is. It's just a deformation, a permanent deformation, and it happens under a static load maintained for a period, okay? Period means just for a time, okay? For a period of time we're talking about. So you can have your material and put a load, just a force on it, yeah? Not moving, static, and see if it's going to have a permanent deformation. And if it does, we call that creep. tension creep. So the creep or deformation due to tension. And we call that failed by rupture, and that's your knacking and your fracturing. So if you deal with knacking and fracturing, so these are deformations, you're dealing with your tension creep. All right, more tests, and that's impact tests. So they determine the energy. And what kind of energy? So it determines the energy required to completely break a specimen. Yeah. So how much energy we need to break a specimen that we're testing. So this energy is called impact toughness of that material. Oh, it's really tough. I can't break it. Okay. Oh, this is this much tough because it breaks at this and this right time and this force. Determine the transition temperature of the materials. We also use this impact tests to determine, again, the transition temperature of the materials. I've told you many times about how important the temperature of the materials, and when you think of the temperature, don't think about the digital value. Okay, that's not your temperature. You have to be able to understand the internal structure of these materials are moving. Okay, moving to some degree. Of course, not at your rate, not at your level. They have their own life. Yeah, not the kind we have. Ours is a biological life. There is a material life. And material, they are also living and they are moving. Okay, they move with the environment. Okay, and that movement we call that temperature. Yeah. Failure and fracture. So that's just the material behavior subjected to, of course, deformation. If you have no deformation, you won't have like failure or fracture. So these are all failure and fracture. Okay, usually you can get them since our textbook is dealing with a lot of metal in this first few chapters. So during metal working operation, you can be able to deal with these failure and fracture. Okay, they're just again deformations. Ductile fracture, characterized by again plastic deformation. Don't forget the word plastic because we're dealing with ductile, you know? So ductility, flexibility, something like plastic deformation. So preceding the fracture. So it is characterized by plastic deformation. It's not a brittle deformation, it's a plastic deformation preceding fracture. So in order to get those this kind of deformation, you require definitely a lot of energy, okay, considerable amount of energy. Brittle fracture, which is opposite to your ductile fracture. So what is it? It's catastrophe. Definitely not preceded by plastic deformation, not like in ductile fracture, and moreover, it requires much less energy than does ductile fracture. Okay, so for ductile fracture, you need a lot of energy. For brittle fracture, you don't need. Okay. Impurities, inclusions, voids. So again, these things they definitely play major role to the fracture of the material or deformation of the materials. They're not very good. Okay, they mess up the material and they definitely induce fracture in the materials. So we want to get rid of them as much as we can in every stage of manufacturing. Okay. Residual stresses. So they remain. It's called residual because they remain in the workpiece. okay, after it has been plastically deformed. We are doing plastic deformation in order to shape them, okay, don't forget that. So in manufacturing, you got to plastically deform your material to shape them in the way we want it in our product. So these residual stresses, they remain in that workpiece, okay, after we deform them, and also after it has had all external forces removed, okay. We use the force, we deform it, we shape it, okay, and then we remove the forces. Even if you remove it, you still have residual stresses because they remain in that workpiece, okay. So every time you think about residual stresses, you will think about that, okay? Okay, so surface tensile residual stresses, they're very undesirable. We don't want them. So we want to reduce them or we want to eliminate them. So what do? We anneal, okay, to get rid of it. So we call it stress relief annealing. We deform furthermore, so further plastic deformation, and we relax them. So relaxation over time or a period. So that's all for your, I think this is, what is it, chapter 2, I guess, yeah. It's all about your mechanical properties, behavior, testing, yeah. Try to understand each test and what are we using for in this manufacturing properties materials. Okay, I'm gonna go ahead and stop here.